So today I want to introduce some of the work that I've been doing on federated learning, more concretely on the security aspects of federated learning and how to defend against certain type of attacks that can happen at training time. So as I assume that some of you perhaps are less familiar with federated learning and AI, I want to give you first a little bit of background about federated learning. So federated learning has emerged as a very important paradigm for training machine learning models in a distributed fashion, so that different participants can collaboratively train a machine learning model without sharing their training datasets. And this is very important and very useful in many practical applications where because of oncoming regulations on privacy or existing regulations on privacy like the GDPR, or because of the nature of the data, participants cannot share the data. So they can leverage federated learning to do it in a private way. There are two main typical use cases. On one side, we have cross-silo federated learning, where we can assume that we have a reduced number of participants that have large data sets. For instance, imagine a set of hospitals that want to build better AI tools for diagnosis, but cannot share the data from the patients. A cross-silo federated learning approach is suitable for this case. On the other hand, we have scenarios where we have millions or hundreds of thousands of participants, for example, using mobile devices, where we can leverage the computational power of those devices without the need of centralizing the data from all those users. And there's actually a success story from Google, which is Google Gboard, is the predictive keyboard that uses federated learning at the core of it. So in a nutshell, federated learning works in this way. We have a server or an aggregator or an orchestrator, call it as you wish, and we have the different clients or the different participants in the federated learning task. At each training round, what we do is the server shares a global model with all the participants in the federated learning task. Then each participant trains the machine learning model locally using their own training data sets. Then, after some training epochs, the participants send back the models that they learn during these training epochs back to the server. So not necessarily all the clients have to send back the model to the server. There are different strategies, but for the sake of simplicity, let's assume that all of them send back the parameters to the server. And finally, with that information, with those new parameters sent by all the clients, the server aggregates the information in some sort of way. Typically, standard aggregation methods includes computing the weighted average between the parameters sent by all the clients. And with that, we have a new global model, a new version of the model that would be shared again with the clients in the next training round. So we would be repeating the same process again and again for a given number of training epochs until the training round, until the model converges. Now that we know a little bit about federated learning, let me introduce you the security problems inherent to machine learning algorithms and to federated learning models in particular. So in these slides, I'm talking more generally about the vulnerabilities of machine learning models. So we can characterize the threat model across different axes. Here I included three main axes, which is on one side the attacker capabilities, the attacker goals, and the attacker knowledge. Given the attacker's capabilities, we can differentiate between two main types of attacks. On one side, we have causative attacks, where the attacker can influence the learning of the learning algorithm in some sort of way. That happens during training. Examples of that are poisoning and backdoor attacks. And on the other hand, we have exploratory attacks, where the attacker cannot influence the learning algorithm, but try to evade being detected or to produce some errors on the system without direct manipulation on the parameters of the model. With respect to the attacker goal, depending on the security violation that the attacker wants to achieve, we have integrity attacks, availability attacks, or privacy attacks. And these attacks can range from indiscriminate to targeted attacks, and depending on the type of errors that we want to produce, they can be generic, so the attacker just wants to produce errors regardless of the type of error that is producing, or specific. So I want just some specific errors to happen on the target model. And then depending on the attacker model, we have perfect knowledge attacks or white box attacks, where the attacker is assumed to know everything or almost everything about the target machine learning system. Although this may be unreasonable for most practical scenarios, from the defensive perspective and for red teaming, it can be a nice assumption to model worst case scenarios. In more realistic settings, we have limited knowledge attacks, and this ranges from pure black box attacks to gray box attacks, where the attackers can have some certain knowledge about some components or some features of the machine learning model, but don't know everything about it. And for instance, in these attacks, we have scenarios where attackers can build a surrogate model in order to compromise a target model, where the surrogate model tries to mimic the behavior and the properties of the target system. In the particular context of federated learning, we need to differentiate between two main types of attackers. On one side, we have outsiders, which are attackers that are not participants in the federated learning platform. So, but still they can do certain things. For instance, if the data is collected from untrusted sources, they can manipulate the training data set of some of these participants to try to influence on the learning process. At runtime, when the model is deployed, as in centralized machine learning, they can try to exploit the blind spots and the weaknesses. For instance, by creating adversarial examples, universal adversarial perturbations, this sort of stuff. Or they may be able to intercept communications between clients and server and infer some properties about the data used by the clients, and perform other types of attacks, like membership influence attacks, for instance. On a more sensitive threat, we have insider attacks, where the attackers are participants of the federated learning task. And in this sense, they can perform stronger attacks. For instance, with respect to data poisoning, they can manipulate a higher amount of training data, or they can manipulate directly the parameters of the model that they send to the server, which is known as a model poisoning attack. And they also can attempt to infer some information from the data set provided by the other participants and perform some sort of property inference attacks. But in this talk, I'm going to focus on poisoning attacks in federated learning, so those that are produced during the training of the model. And the difference with respect to centralized learning is that we can have a broad variety of scenarios depending on the number of attackers and the coordination between the attackers. We can have scenarios with a single or multiple attackers that are not coordinated, or we can have more dangerous scenarios where we have colluding attackers. Colluding attackers can perpetrate attacks at a larger scale with higher impact on the target model. They can achieve higher attack success rate. And the most challenging scenario would be where the one where we have different groups of colluding attackers trying to compromise the system. So with respect to the attacker capabilities and the fact that the attackers can be outsider or insiders, on one side we have data poisoning attacks where the attacker manipulates just the training data points used for learning the models. In the case of outsiders, we can expect that they can have less influence on the model because they can compromise less data points compared to an insider. For instance, if a participant is malicious, it can manipulate the entire training data set and have a bigger impact on the federated learning model. On the other side, as I mentioned before, we have model poisoning attacks, where instead of manipulating the training data, the attacker manipulates directly the parameters that sends to the server. In the case of outsiders, it's a more challenging attack to perform because it requires to intercept the communications between the server and the client and perform some sort of man-in-the-middle attack. But for insiders, it's an easy thing to do, so they can manipulate the parameters as they wish, as long as they have access to the training procedure or the software for training the model. And with respect to the potential harm, the most dangerous attacks are the model poisoning attacks, followed by the data poisoning attacks performed by insiders, and perhaps the weakest attack is the data poisoning attack performed by outsiders. Let me give you the intuition about how poisoning attacks work in federated learning. Let's assume that we have a very, very simple machine learning model with just a single parameter, that we're going to call it beta, and we have a scenario with 4 participants. And in this case, let's assume that all of them are benign. So after doing the local training, each of these 4 clients sends back to the server the parameter they learned for beta. And in this case, you see that all the parameters are between 4 and 5. And if we computed the average, we have an average of 4.5 actually. But let's see what happens if we have an attacker that says that the parameter of beta is not something around 4 or 5, but it's 100. Now, if we compute the average is much higher than it should be. So in other words, what is happening here is that the average is not robust against outliers or against the possibility of having an attacker trying to influence on the value of this parameter. And this problem is more complex in the case of standard machine learning models, because here we have just a single parameter. But in a real machine learning model, we have thousands, hundreds of thousands, and now with large language models, we have even billions of parameters for our machine learning model. So it becomes a more serious threat. So we need to resort to something smarter to be able to filter out these attackers or this behavior from outliers. Let me show you a couple of defenses that have been proposed in the research literature. On one side, we have CRUM, which is a function for a robust aggregation function, where for each client, we need to compute the distance between the parameters or the gradients that are sent by the other clients. So we need to compute a pairwise comparison for all the clients. Then we compute a score called the CRUM score, which is the square sum of distances between the closest neighbors, given by those numbers. I don't want to get into too many details, but those numbers depend on how many attackers we assume that we can tolerate, and what is the total number of clients, of participants that we have in the federated learning task. And then we pick the client with the smallest CRUM score. The problem with this approach is that at each training round, we just pick the updates from one single client, which is really suboptimal. So because we are not capturing the knowledge from all the benign clients that we have. There is a way to mitigate this problem, which is using multi-CRUM. It's a variant of the algorithm where instead of choosing just a single client with the lowest CRUM score, we pick M clients with the lowest score. We need to be mindful that M cannot be very, very high. Otherwise, we may be including some malicious participants in our aggregation. But again, it has limited scalability with the number of clients, because we need to compute a pairwise comparison, and if we have scenarios with millions of clients, it doesn't scale well. On the other hand, we have coordinate-wise median. So as I mentioned before, computing the mean or the average is not robust against these attacks, but computing the median for each one of the parameters provides a robust estimator of the parameters for doing the aggregation in the server. There are variants where we can compute the trim mean. The trim mean means that we eliminate the most extreme values for each parameter on the upper and the lower bound side. But computing this, again, can slow down the time to compute the aggregation, especially in cases with cross-device settings with hundreds of thousands of users, for example. And on the downside, it doesn't really allow to identify the malicious participants. Now, let me introduce you adaptive federated averaging. That is a technique that I proposed with some of my previous colleagues at Imperial College London, where we try to address some of the limitations of the previous methods. So we realized that we can reduce the computational complexity by computing the similarity for each client with respect to a reference model. Instead of computing the similarity with respect to every single client, we compute similarities with respect to a reference model that in our case is a tentative aggregated model that we compute at each training iteration. Then we rely on the assumption that the similarity value for the benign clients should be somewhat similar. And that allows us to identify malicious clients. And we can block that clients that's consistently send bad model updates to the aggregator. Let me show you a couple of examples of how adaptive federated averaging works without going into the mathematical details of the algorithm. So let's assume that the client send the parameters back to the aggregator. Then we compute an aggregate model and compute the similarity of all the clients with respect to this aggregate model, which takes linear time to compute. Then we have the similarity values, which is a single scalar. We can compute the Euclidean distance, the cosine similarity. And then we compute the mean, the median, and the standard deviation of these similarities. So the median is depicted in blue, the mean is depicted in green, and the yellow interval is given by a scale version of the standard deviation. We have a parameters that give some slack on the uncertainty about this similarity. So based on the standard deviation, we can make it a bit bigger or a bit smaller, depending on how strict we want to be with the detection algorithm. So what we do is the following. We look at the position of the mean with respect to the median. In this case, the mean is higher than the median. So we're looking for model updates that are influencing the model in a negative way and are trying to increase the value of the mean. And we're looking for those values or those clients that have a similarity value outside the interval depicted in yellow on the right. And we found one malicious client. So we eliminate that client and we recompute the aggregation rule. Let's see what happens if we have different groups of colluding attackers. We follow the same procedure. First, we compute the similarities, then we compute the median, the mean, and the standard deviation, the scale standard deviation. We look at the position of the mean with respect to the median. So again, the mean is higher than the median, so we look to the right. And we look for those updates that are outside the confidence interval, and we find one client. So we eliminate that malicious client, and we repeat the process. We have now these 6 clients. 2 of them are still malicious. So we compute again the similarities, the mean, the median, and the standard deviation. And we observe that the mean now is lower than the median, so we look to the left. And we look for the model updates that, again, are outside the confidence interval. And again, we find that there are 2 clients there, so we remove them. And what we would do is we repeat the process until no clients are removed. Then the other component of adaptive federated averaging is the modeling of the behavior of the clients. For that, we use a hidden Markov model where we're trying to infer what is the probability or distribution of each client sending benign model updates. So we have 2 random variables here. The observer random variable, O, which represents the outcomes at each training round of the detection mechanism that I explained before. So it's a Bernoulli random variable that is telling me the update at this training round is good or is bad. And then we have the variable G, which is the variable that I want to infer. And based on a prior distribution on G0, that I have for each client, and we're using a beta distribution to model that, we can compute at each training iteration what is that probability distribution of a client sending good or bad model updates. And at some point, if we observe that the distribution is very skewed towards 0, so the probability of the client sending good model updates is very, very low, we block the clients and we stop communicating with that client. Let me show you a simple example so you would understand. Let's assume that we have this scenario that we had before with 4 participants, and one of them is malicious. Before we start the training, the probability distribution that we have for each client is given by the prior. And with the prior, we put an informative prior, so we don't make any assumptions on how good, how bad the participants are. We could, if we had previous information from previous Federated Learning tasks, we could include somewhat that information. But in our case, for the sake of simplicity, we assume that the prior for everyone was the same. So with that, we see that all the distributions are centered around 0.5. So the probability of sending good updates is half and half. But as soon as we start doing the training, so the malicious client sends malicious model updates. So when we update the probabilities, for the probability for the good clients shifts to the right. So the mean of the distribution is greater than 0.5, and for the malicious client is less than 0.5. So we repeat that. It could happen that at some point we have some false positives. So for some clients we detect them as malicious for a single model, a single training run. But if we continue the training and the malicious participant sends consistently malicious model updates, at some point you realize that the distribution of the malicious participant is quite different compared to the benign ones, and the score or the average of that distribution skews more and more towards 0. So at some point what we do, following a probabilistic rule based on the cumulative probability distribution for each one of the clients, we decide to block the malicious participant. So with that, we also improve on the communication efficiency, because we don't exchange information with that participant anymore. And on the other hand, we also reduce the burden and on the aggregation side. Let me show you some experimental results on some machine learning benchmarks. 3 of them are computer vision, MNIST, fashion MNIST, and CIFAR. We perform different type of attacks, from label flipping attacks to Byzantine attacks and noisy clients. And we tested the standard federated averaging and the robust aggregation methods that I explained before. So what we show in our experiments is that when there's no attack on the clean scenario, things are okay for all the robust aggregation methods, except for multicrum that provides a bit worse results. But especially for the label flipping attacks, what we observe is that the robust aggregation methods are not capable of mitigating these attacks. On the contrary, they are quite unstable and oscillate quite a lot. In the table, you can see that consistently adaptive federated averaging, denoted by AFA, in the tables, perform consistently better and is capable of mitigating the effect of the attacks in all cases, whereas some of the other robust aggregation methods fail, as mainly in the label flipping attack. Then about the malicious client detection, we observe that our method is very, very good at detecting the malicious clients, except for the noisy participants, where the malicious participants just add noise to the server, where in some cases, for CIFAR 10, the detection methods is not very good. But to be honest, the effect on the results on the Federated Learning model are negligible. So the attack has very, very little effect there. So we are just filtering the most harmful attackers, and the results are as good as with any other robust aggregation method. Then, by looking at the computational complexity, we realized that, as we expected, that our method is much faster than the other competing methods. Computing the median or computing the similarity, the pairwise similarity for all the clients as in Chrome is very ineffective. And in this case, we did it with 100 clients. Imagine that you have 100,000 clients. So the difference is remarkable. Some limitations and lines of improvement. So in the scenarios that I showed before, we consider IID partitions. So the data is distributed identically across the different clients. But if we have the heterogeneity, the problem is that the variance of the client similarity increases. Our preliminary experiments show still that we are capable to resist to these attacks, but having more variance means that we have higher risk of having false positives, and it could be more difficult to detect stealthier attacks, trying to be less aggressive than the attacks that I showed before. Yeah, just 1 minute. Then about the robustness against stealthier attacks. Nowadays there are very advanced attacks against federated learning systems, and adaptive federated averaging can be vulnerable to these adaptive attacks or these stealthy attacks. The weakness is that we are looking at the similarity considering all the parameters, and that can be a bit ineffective. The way to sidestep this problem would be to look at the specific layers, and perhaps making layer-wise comparison to be able to detect more targeted attacks. Just as a final point, so hope from this presentation you realize that model poisoning is perhaps the most relevant threat to attack federated learning algorithms, especially during training time, and the robust aggregation techniques are really needed, because standard aggregation is very brittle, not only in the presence of an adversary, but also in the presence of faulty users. But robustness can have a price. So what happens if we have a lot of data heterogeneity in the data provided by the participants? So there's kind of a trade-off between robustness as accuracy. But we think that adaptive federated averaging allow us to come up with, or to overcome some of these problems, allow us to detect the bad model updates, and so detect attackers or faulty clients, and to model the behavior of the clients over time. And also it reduces the computational complexity with respect to other competing methods, which is very nice for cross-device settings. Thank you very much for your attention. Again, it's been a pleasure. I don't know if we have time for questions, but otherwise I'll be around the whole day. Thank you very much.
I think we do have time for questions, if there are any.
Sorry, yeah, just following up on the, a really nice idea of the distribution shifting. Can you also keep a history? So in other words, if I see the distribution shifting, can I go back and look and see how many times do I think you were, like, or is that too much to store for each?
You can compute that information. Actually, you could have kind of a window. In our case, we consider all the iterations, all the history of the client, but you can also consider some smaller window of the history of the participant. But yeah, you can keep track of at which iteration that each client provided a good or a bad model update.
And then use that as part of your decision.
Yeah. So this is starting, or it tried to be a model with the most general case, but you can tweak it for considering different scenarios. For instance, changing the prior, if you have prior information about the participants, or using smaller windows to model the behavior of the participants more locally.
Yeah, good. Thanks.
Yeah, which can be interesting, for instance, in scenarios with online training.
There's a question there.
I was curious as to whether or not you could have a hierarchical aggregation extension of that sort of idea. So if you're doing the aggregation, particularly maybe in one location, and you've got models training on multiple devices, but as the complexity and the number of models increases, then you would need multi-hierarchy sort of things in order to aggregate. And I was just wondering how the complexity of the algorithm that you're currently using
Ac-
respond to that?
Yeah, actually, that's a very, very good point. We haven't looked into that yet, but that's a very, very good idea. There, I would say that it's also related to the amount of trust that you have in each element in the hierarchy. So perhaps you can assume that at a lower level, you have more untrusted devices, that as you progress higher in the hierarchy. And perhaps you can leverage that to tweak or to adjust how strict you are when accepting or rejecting a model update coming from one entity at the hierarchy level. But indeed, it's a very, very good idea, which is especially relevant nowadays for many cross-device settings. Yeah.
And another question is that, so in a heterogeneous data environment, so models have different knowledge about different circumstances, which may mean that they are giving suboptimal solution to this particular problem because they're training a different data set. So if the model is perhaps trying to move towards some sort of global minimum, which with respect to its own data set, it's going to try to move there, whereas you're saying, no, you're missing the local minimum of this particular data set, that's what you're doing wrong. And I was just wondering if you have any comment on excluding experts that are looking at the problem in a totally different way and confusing them with malicious actors.
Yeah, that's the main challenge with robust aggregation, that you have this trade-off between robustness and accuracy, especially for capturing the novelty of some model updates provided by participants that may have very, very good insight about some data points. And the problem is that if those updates are quite different from the consensus or from the general consensus from the other 9 participants, it's quite likely that you identify that as an outlier. So it's the trade-off that you have, and it's very difficult to come up with a solution that allows you to detect what is a genuine novel update or what is a malicious update, especially when you deal with the more targeted attacks. So it's one of the downsides of robust aggregation. You need to take into account this trade-off between robustness and accuracy. So there's no free lunch here.
That's where some prior information might come in handy as well. If you knew that.
Yeah. You could use that. Actually, that was our idea of building this reputation score with the clients, because you can use that for those type of corner cases. So yeah, perhaps it's a solution. But if you think of smart attackers, they can try to evade that by building a good reputation and they performing the attack.
Yeah.
So it still is challenging.
Hi, you mentioned a layered approach rather than parameters. Can you touch more on why would you prefer layered?
Yeah, because you reduce the dimensionality of the problem. So instead of computing the similarity with respect to millions of parameters, you just compute the similarity with respect to 100. So the similarity value that you are going to get is perhaps more informative. And you can think of that, for instance, for detecting some backdoor attacks that tend to operate more in the final layers of the machine learning model. So you can look specifically at that. But the problem is that if you just do that, maybe the attackers can leverage the weakness of your model and try to influence more on the earliest layers. But the idea is try to reduce the dimensionality and find more local analysis of the variations of the model across layers. So that helps to detect more subtle attacks. But how to coordinate or how to do a whole analysis of taking into account the similarities with all layers, it needs to be taken carefully.
Louis,